All right, we're going to talk more about hypothesis testing. Now, it's common in hypothesis testing to hear about type 1 and type 2 errors, which are just about the most boring possible labels, but they are important. It's just, statisticians and econometricians are not really interesting people. Sorry. Since there's inevitable randomness to the outcome of a hypothesis test, this little table here might help. There are two possibilities in the row. Either we reject the null hypothesis or we do not reject the null hypothesis. Then the vertical columns, we have two possibilities. Either the null hypothesis is true or the null hypothesis is false. If the null hypothesis is true and we do not reject, that's a win. It's good news. Alternately, if the null hypothesis is false and we reject the null hypothesis, then again, win. But those off diagonals, oh poop, we've screwed up. If the null hypothesis is true and we reject it accidentally, that's a type 1 error. In our dice example, the null hypothesis is the dice is completely fair. Rejecting it would be a case like my fair dice just happened to roll more sixes than I might have expected, and I conclude, oh, those are unfair, even though the poor things actually haven't done anything wrong. The other off diagonal is type 2 error, where the null hypothesis is in fact false, but I do not reject it even though I should. Back to the dice example, that would be a case where maybe I've shaved off one side. It's slightly different probability of rolling a 6, but in only maybe 20 rolls, I don't have good power. I cannot reject the null hypothesis conclusively. I can't say for sure that it's not fair. When we set up hypothesis tests, we can choose the level of significance, the probability of making a type 1 error. That's where the choice of 5% comes from. We can control that part. We cannot control the probability of type 2 error because that depends on how close is the null hypothesis to being true. In our dice example, if I do just a little bit of shaving or something, maybe 6 is maybe 1 percentage point more likely to come up. It would take an awful lot of rolls to be able to recognize that. If I don't roll enough, I don't get enough data, I might not reject the null hypothesis the dice is fair, even though that's actually an error. As in all of economics, there's a trade-off. The lower we drive down the probability of type 1 error, the higher, therefore, type 2 error probability must become. Now, often our tests are comparing samples. We might ask, is there a difference in the means? Asking if two means are equal is the same as asking if, when I subtract one from the other, do I get 0? Now, of course, they're never precisely 0, but we want to know if the difference is big. How big would the difference have to be for us to say that, oh, that's a big difference? To create that hypothesis test, we would find the standard error of the difference in the means. With x bar 1 and x bar 2 representing the means of each group, standard errors of S1 and S2, then we use the formulas about linear functions and show that as long as those are not correlated, as long as those outcomes in the two groups are indeed independent, then the standard error of the difference is going to be the square root of the sum of the variance, not the standard errors, variance, divided by each n. Sometimes you see other formulas, I think on Hawks they go through some of those, that if you're willing to assume the standard errors are equal, then you could use a different formula. But that gives rise to a question, how would you know that? Why would I think the means are different but the standard errors are identical? It's kind of a strange assumption. Generally, it's more conservative to estimate each different standard error. Then the tests are going to be a little more conservative, trading off between type 1 and type 2 error. Now, another thing that commonly gets done in Principles of Stats, you're shown how to construct a one-sided test, where instead of saying what is the probability that I could see a measure as big as some number, where big is an absolute value, we ask the easier question, what's the probability that I could see a measure as big in just one direction, and only one direction? In those little pictures, that's the light purple shading, not the dark purple shading. Now I'm not adding together both tails, instead only using one of the tails. And the total shaded area is going to be lower in the bottom picture with the lighter purple. A one-sided test is just not as rigorous. Now, it is formally correct to do that, but still for me personally, whenever I see a one-sided test, that raises red flags. It's kind of shady. It's usually admitting that the data is not that clear. I mean, whatever. There may be cases where it's legit, but for me, like I said, personally, I just find it shady. Now, in most hypothesis testing, there are three main methods you commonly see, but it's worth reminding they're all formally identical. We can do some mathematics to demonstrate. Either I calculate x bar, the mean, and its standard error to see if it's greater in absolute value than some critical value, such as 1.96 for the 5% level. Or I could calculate the confidence interval, which is 1.96 times the standard error, plus or minus, and see if that includes 0. Or I could calculate the p-value, which is the lowest possible probability that would reject the null hypothesis, and determine if that is less than my significance level, typically 5%. They're all getting the same place. They're all doing the exact same thing, but it can be confusing because it seems like they're very different approaches, but they all get to the same outcome. Now, one of the places where we ordinary people would see confidence intervals is polling. Suppose some policy or politician is given as some level confidence interval plus or minus 2 percentage points. Now we can figure out where are they getting that confidence interval from. It's actually easy since the fraction of respondents who answer yes, p, is distributed binomial, so the standard error there is the square root of p times 1 minus p divided by n. Typically, p is going to be near 50% because most polls are looking at issues that are controversial with people on both sides. An interesting poll, therefore, is going to have a probability close to 50%. And that's where the standard error has its maximum. So if you want to be a little conservative, then the standard error formula set p equal to 0.5. Then the standard error is going to be pretty much determined by the sample size. A poll of 100 people would have standard error 0.5 divided by square root of 100. That's 5%. If I poll 400 people, that's 4 times as many. Square root of 4 is 2, so that has half the standard error. If I want to have a poll that has confidence interval plus or minus 2%, then just solve for n in that little formula there. It takes about 2,400 people. You could shave that down a bit, and I'm sure people do. But if you're in the polling business, your pricing is basically determined by how accurate the client wants the answer to be. Client wants a poll. Your basic question is, okay, how accurate do you need? Do you want that plus or minus 2% or something else? Then we got to find almost 2,500 people to answer the poll. If the client would be happy with plus or minus 3%, then we could sample fewer people. If they want plus or minus 1%, then we've got to sample more people. Typically, the costs are going to scale up with the number of people who are polled. And that's the business model right there. Now you should be able to work out this apparent puzzle here, what I've called a devious poll. Overall, if I look at just the total sample, I can see the support in favor of some candidate is 170 people out of 300, and that is statistically different from 0 at the 5% value. But if I have 3 subgroups, maybe people in neighborhood A, neighborhood B, neighborhood C, then none of the individual subsamples are statistically significant. Which is a reminder that statistical significance is not linear. A p-value of 4.9% is called significant. A p-value of 5.01 is called not significant. That can produce these weird, non-intuitive effects. Part of your stats education is drilling yourself to develop an intuition for how these things work and how people are going to try to play you with that. Now, another sort of shady thing that people will do is a series of tests. Every statistical test has some probability of error. Type 1 error, like I said, often chosen to be 5%. That means if you do several tests in a row, the second test depends on the outcome of the first test, and the third test depends on the outcome of the second test, which depends on the outcome of the first test, et cetera, then your error is going to compound. With 2 statistical tests, if each one has a 5% chance of type 1 error, then the probability of not making a type 1 error in either one is 90.25%. So that nearly doubles the type 1 error. The test significance is no longer just 5%. 3 tests, my significance is going to be 15%. I've nearly tripled it. 10 tests, the significance level is just 40%. That just gets bonkers. I mean, that's completely terrible. Now, the worst part, a lot of computer stats programs have automated routines that will test every group and subgroup to find a, quote, significant, unquote, difference. But that's no longer actually the advertised statistical power. You're doing a series of different tests, so buyer beware. Now, sometimes people do this knowing they're doing it wrong. Other times people do it and don't even quite realize that the testing just doesn't quite work the way they think it does or should or whatever. I mean, I'm kind of down on canned tests in general, I have to admit, because I found for a lot of students, they're looking for a shortcut and they don't get the understanding what's actually going on. I mean, I've asked questions on an exam where the difference in the mean is completely opposite sign what we'd expect. And yet students will go through and plug in the test because they think they know what they're doing. They think they're just plugging values in a formula. And the computer's even better than you at plug and chug. At no stage will the computer go, that's kind of weird. So while R has plenty of canned tests for t-tests and chi-square tests and all the rest, I would be very cautious about using those too early in your journey. Shortcuts can just end up taking even longer. Now, the final detail about doing hypothesis tests is with a small sample. Our test statistic for a mean is going to be x bar divided by s over the square root of n, where I'm estimating s. In a large sample, that estimate of s is going to be good enough. I don't have to worry about it. But in a small sample, I have to worry about the additional variation from that estimate as well. Now, you're perhaps estimating how small is small. Just like previous questions, how big is big? But in this case, we have a simpler answer. Typically 30. 30 observations is a small sample. More than that will give us sufficient degrees of freedom. If you're using smaller samples than that, then a test statistic has a t-distribution. You can see in the picture the t-distribution depends on degrees of freedom, and with fewer degrees of freedom, excuse me, has fatter tails there. That changes the critical value. The normal distribution is a critical value of 1.96 that provides a 5% chance of type 1 error. That's the bottom row of the table. As you read up, in that first column, it's 1.96. At the bottom, it's a lot of observations. But if you only add like 5 degrees of freedom, then the critical value would be 2.57. That's, a good bit bigger. From 30 degrees of freedom, then, the critical value is 2-ish, which is generally close enough, but just something to be aware of when you have a small sample.